Hello everybody. So I wanted to make a supplementary video here about deMorgan's laws because it seems like that's one of the more conceptually difficult things here in the 1.1 notes, and I think that just arises from the fact that it might be difficult to see exactly what we do with deMorgan's laws or why we use them or when we use them. So I want to do a little bit of a supplement here. I want to talk a little bit more about why and when we use deMorgan's laws. It's more of a tool and a technique for us than anything else. And I also want to redraw those diagrams on page 8 in the 1.1 notes to hopefully help clarify what deMorgan's laws allow us to do and why we would use them. So again, what I'm referencing here are deMorgan's laws on basically the last 2/3 of page 8 in the 1.1 notes, which is video 4 in the recorded lectures. So when we think about deMorgan's laws for the purposes of this course, these are really, again, a tool or a technique that we can use. And specifically, we use deMorgan's laws to translate what I call a tricky probability expression into what I call a nicer probability expression so that it's easier for us to compute the probability we want. So basically, deMorgan's laws are a tool that we can use if we have a certain form of a tricky expression. We can translate that into a nicer expression. What I mean by a nicer expression, as we'll see here in a second, is one where it's a lot easier for us, in most cases, to either visualize that probability or just calculate it. So that's the whole purpose of deMorgan's for us. It's a tool that we can use when it applies. And so again, I'd like to go through those three main deMorgan's laws on page 8 and clarify when deMorgan's laws might be useful. So let's go ahead and look at the first one here. So this is the first of the deMorgan's laws listed on page 8. It tells us that this expression is equivalent to this expression. In other words, these two probabilities are equivalent. So let's take a look at this side of this equality. And let's just ignore probability for a second. Let's just think about what this is. This is the intersection of A complement and B complement. And if we just kind of think about what that is visually, or even probability-wise, even if we think about calculating that probability, that's kind of hard to think about what that is, especially in like a diagram, right? If you think about the intersection of complements, that seems kind of strange. That doesn't seem very intuitive as far as what it looks like in a visual like this. So this is something that I would call a tricky probability expression because we can't really easily, at least I can't, easily see what this looks like in a picture. But if we consider this part, the thing that's equivalent to that, I would say that this is a much nicer probability expression because this, as we'll see here in just a second, is a lot easier to visualize in a diagram and is often, at the same time, a lot easier to calculate. So let's actually go ahead and visualize both of these probability areas or both of these regions. And we're going to see first that these two things are in fact equivalent if we were to draw what they look like in a Venn diagram. And we're also going to see that this is actually a much easier expression to actually calculate based on some of the other rules that we have. So let's take the tricky side and look at that first here. So here I'm just going to graph what this looks like. I'm going to draw this area in this sample space. So kind of like I have in the notes already, if I think about A complement, I'm going to shade that in red. So A complement is everything that's not in the red circle. So if I shade everything that's not in the red circle, that's going to be A complement. B complement is the same idea. It's just now everything outside of the B circle. So I'm going to shade that in blue. So everything not in the B circle is B complement. Okay, so now what I want to do is I want to see what this is. So I have these two areas shaded now, A complement is shaded in red, B complement is shaded in blue. Now I want to say, okay, well, what's the intersection of that? What area represents the intersection of those two regions? And I'm going to highlight that in, let's see, does the blue show up here? Yeah, let's use blue. I'll switch this to that highlight. Okay, so the intersection, remember, is our AND event. It's everything that's going to be in this and in this. So it's everything that's shaded both with the red and with this blue. Actually, let me switch my highlighter color so I don't get us confused with colors. Let me switch this to, let's switch it to green for now. So for the intersection here, I'm going to shade everything that's both red and blue. So that means I'm going to shade everything that has both the vertical and the horizontal shading, the red and the blue shading, which is all of this stuff. So this represents this whole expression. It's the intersection of A complement and B complement. So that took a little bit of thought, right? It took a little bit of thought for us to say, okay, well, I have to shade this area for A complement, this area for B complement, have to shade the intersection there. There's a bit of work. Now let's look at this one over here. So here we're shading the complement of the union of A and B. Now, if I think about the union of A and B, that's a bit of an easier region, right? A union B is everything in A or in B or in both. So if I think about this union region, I'll use purple, that's just going to be everything in the circles. So this is my A union B. And now if I think about the complement of that, that's a lot easier to, I think, conceptualize than this thing, because now we say, oh, well, the complement of an event is everything outside of that event. So the complement here is going to be everything outside of our shaded region. And if you'll notice, this region in this graph that I'm shading in green is going to be the exact same region I shaded in green in my first graph, which means that, as deMorgan says, this area, and therefore the probability, is equivalent to this area, or this probability. So deMorgan's is useful because, as we saw, we started with something that was tricky, both visually and probably calculation-wise in a lot of cases, and we translate that to something like this, which is a lot easier to visualize and a lot easier to calculate, because if we think about what this thing is equivalent to, using the complement rule, this is 1 minus the probability of A union B. So all we actually need to know to calculate this probability is A union B, because deMorgan's tells us that this ugly looking thing is equivalent to this, which is a lot easier in most cases to calculate. And we can do the same sort of thing for the next piece of deMorgan. So the second deMorgan's law here tells us that this guy is equivalent to this guy. Okay, so let's do the same sort of a thing. Let's shade and see if we can kind of understand how they're equivalent, and then talk again about the usefulness of deMorgan's. So here I have A complement again. I'm going to go ahead and shade that in red again. So that's everything outside of my A circle. And then I have B complement again. That is everything outside of my B circle. I'll shade that this way. So everything that's not in B, I will shade, because that's the complement. And now the thing, the operation, the word that's joining those two things is the union. A complement union B complement. And again, if we kind of think about that, even with this shading, it might take a second to think, well, what is that? What does that mean in terms of this picture? Well, since this is a union is our or. So this is going to be everything in A complement or B complement or both. In other words, in this picture, it's going to be everything that's shaded at least once, right? Because everything that's shaded at least once is either in A complement, red, B complement, blue, or in both, shaded with both colors. So the union of A complement and B complement is actually going to be all of what we saw in the previous question, so everything that's shaded twice. But it's also going to be everything that's shaded once. So it's going to be this piece as well, since that's shaded in red, and this piece as well, since it's shaded in blue, right? Because or, with a union, is everything in A or B or both. So in this case, everything in A complement or B complement or both. So it's the same sort of an idea. We started with something that looks kind of tricky, and conceptually it's kind of tricky as well. It might not be as intuitively obvious as far as what that looks like or what that area represents. But now let's take a look at this piece, which deMorgan's says this area, and thus the corresponding probability, is equivalent to. So here we have A intersect B, and that whole thing complement. And it's very similar to what the first deMorgan's law tells us as far as what this looks like. So here we had A union B up here, complement. Here we have A intersection B complement. So I'm once again going to start with the thing that's being complemented, the A intersect B. A intersect B is everything in A or in B, sorry, everything in A and in B. So that's just going to be this little piece here. Actually, let me be consistent with my shading here. Which means that when I apply the complement, that's going to be everything outside of that shaded region. And we're going to see, once again, that the area in green that I'm shading in this second diagram is going to be equivalent to the area in green that I shaded in that first diagram right next to it, which visually means that these two areas are equivalent. This area in green here is the same as this area in green here. We just got to it in a different way, which means that the corresponding probabilities are the same. So for this deMorgan's law, what we did is we took this tricky looking expression, and by deMorgan's we said, well, that's equivalent to this, which is a lot nicer. And it's a lot nicer to calculate because, again, it's a complement of something. And so this, using the complement rule, is the same as 1 minus the probability of A intersect B. So by knowing deMorgan's, being able to apply deMorgan's, we can actually calculate this ugly looking thing by just knowing the probability of the intersection of A and B. deMorgan's allows us to make the jump from this to this, which is typically a much easier calculation. So again, the whole idea behind deMorgan's is taking something tricky, this or this, and translating it into an easier to calculate expression, this or this. So of course, if you're starting with something like this, you don't have to use deMorgan's. I mean, you can if you want to, but typically this thing is easier to calculate than kind of working backwards and calculating this equivalent statement. Same here. If I'm starting with this, if this is the thing I need to calculate, I could go and use deMorgan's and use this equivalent statement here. But again, typically this piece is easier to calculate and visualize and everything else compared to this piece here. Now this last one here might not be quite as easy, or it might not simplify quite as much as those previous ones, but this one still, again, kind of goes into this idea of making things easier to calculate overall. So let's take a look at this piece of this expression here and see what that looks like. A complement union B. A complement is everything outside of our A circle, so once again, that's going to be everything shaded in red here, everything outside of that red circle. And here is just plain old B, so that's going to be everything in our blue circle. And so if I think about the union of these two things, again, union is our union is our or statement, so everything in A complement or B or both, which again means everything shaded in red or blue or both. So for this union, I'm going to shade everything that has either the red shading, the blue shading, or both shadings. And so the only thing that's not getting shaded is that piece of the A circle there that doesn't have any red or blue in it. Now, sometimes this is easy enough to find. It depends on the problem, depends on the information that you have. But deMorgan's tells us that this is equivalent to this. And so if we think about, again, what this is, what this represents in a picture, we can kind of do the same thing. And I'm actually going to shade this in a little bit more detail as well, just to make it easier to see. A is everything in my A circle, so this. B complement is everything outside of my B circle, so I'll shade that in blue. And then if I think about the complement of that, actually, let me think about this intersection first. So let me use a different color here for the intersection. The intersection of A and B complement, intersection is our and. It's going to be everything in A and in B complement. In other words, it's going to be everything shaded red and everything shaded blue. They have to be shaded by both. And the only region that's shaded by both the red and the blue is this region here. Right? Because everything else either has no shading or just red or just blue. The intersection means we need both shadings to be in that intersection. And now if we think about the complement to that, the complement is going to be everything that's not shaded yellow, right? The complement of this intersection is everything not in the intersection. And so again, what we're going to see is this area that I'm shading in green here on the right side, the right diagram, is going to be the same area as what we shaded in the left diagram. So everything that's not shaded yellow gets shaded green because that's the complement. And we can see that that shaded green area on the right is the same as the shaded green area on the left, meaning that these two statements, these two regions, and thus the corresponding probabilities are the same. So if you happen to know what this probability is, you can calculate this pretty easily because, again, this is just the complement of that intersection of A and B complement. So this just becomes 1 minus the probability of A and B complement. Now, again, this last one doesn't simplify quite as nicely as the two ones above it. So this side and this side of the right side of the two previous diagrams are a little bit visually simpler than this one, but it's still another way of finding what might look like a more complicated probability. Because typically intersections are easier to work with and easier to compute than unions. And so here we're basically reducing a union statement to a statement involving an intersection and a complement. And those are typically a little bit easier to work with and visualize and calculate than unions. Not always, but typically. Okay. So again, the whole point of deMorgan's laws for us is it is a tool. It is a technique that we can use when we have tricky expressions like this, or this, or this, and we want to use deMorgan's to translate these into easier to compute or easier to work with statements like this, or this, or this. So you don't have to use deMorgan's. You never have to use deMorgan's unless you don't have enough information to do one. Maybe you don't have enough information to do this, but you have enough information to do this. But if you can calculate this thing without having to use deMorgan's, that's great. That's fine. But if you see something like this and you're like, oh, is there a way to simplify that? Or is there a way to rewrite this kind of an expression to look nicer? deMorgan's is a good technique to do that, to make the calculation, the probability calculation, a little bit easier.